Thank you, Andre, and good afternoon, everyone. My name is Aged ICs. I'm one of the faculty in the department, and it's my pleasure to introduce two new colleagues we have in the department, Professor Junsheng Zhang and Professor Abesta Sasan. You see the title of the presentation on the slide. In the interest of time, maybe I can ask Professor Zhang to start sharing his slides, and I make a brief introduction before turning it over to him. Dr. Zhang is a professor in the department with a long list of success and awards in his that he has collected over the years. His research interests fall in the general field of information networks and data science, including edge intelligence, reinforcement learning, continual learning, network optimization and control, game theory with applications in connected and automated vehicles, 5G and beyond, wireless networks, IoT, data privacy and security, and smart grid. Professor Zhang, the floor is yours.
Thank you so much, Sohei. Hi, good afternoon, everyone. I'm honored to have this opportunity to share with you some research ideas in our group. I'm really honored to give this talk right after a touching keynote by our distinguished alumni, Frank. So I hope you find it interesting. So one main focus in our group is on edge AI and its applications in connected and automated vehicles. So I'll tell you what is edge AI and explain why we research on it. Okay, so over the past decade, machine learning AI has received so much interest. So nowadays, pretty much every field, every company, every industry is trying to make use of machine learning to improve system performance, to do something better. Along a different avenue, edge computing has also garnered a lot of attention. Okay, that's because big data is descending from the cloud to internet edge. Okay, so edge computing offers many benefits, including low latency, privacy protection. So the marriage of the two, machine learning and edge computing, gives us edge AI. So when you push AI from the cloud to the internet edge, there are already many applications in the making, such as autonomous driving, Siri, and drone delivery, smart health, other applications. So let me elaborate a little bit. Okay. Yeah. So we're living in a big data era. Okay. Over the course of like 5,000 years, from human civilization to year 2018, 2019, human being generated about 8.3 zettabytes of data. A zettabyte is 10 to 18 in the water. Okay. So over 5,000 years, human being generated about 8.3 zettabytes of data. And it's predicted over the next few years, by year 2025, there will be 175 zettabytes of data at the internet edge. So that's like many, many tens of folds more than the data generated over the course of 5,000 years. Okay, and most of the data actually live at the internet edge. Okay, so if we still use the traditional legacy computing paradigm, cloud computing for model training, model inference is infeasible. The amount of data is just too much to be transported back to the cloud, right? And furthermore, the latency would be not acceptable, right? So many of the AI applications require real-time intelligence. Okay. Okay. So, yeah. So for machine learning, over the past decade, there's been tremendous amount of studies on different learning approaches. Supervised learning, unsupervised learning, more recently reinforcement learning, right? So the marriage of deep learning and reinforcement learning give us deep reinforcement learning. Perhaps when we wake up tomorrow, we have like deeper reinforcement learning. All right. So Edge AI finds greater utility in autonomous driving. Okay, so this is where we want to be. This picture gives us where we want to be in 10, 15 years. So each vehicle functions as a sensor and also as an actuator. Okay, so each vehicle can sense its local driving environment, can share sensing data, control signals with vehicles in the proximity, right? And then in this way, vehicles, they can work in concert, right? They can use Edge AI to work in concert to improve the efficiency, okay, improve the safety. Okay, yeah. So in fact, smart vehicles are emerging as the fifth screen in our everyday life. Okay, so think about it. Which screens in our everyday life? You have your smartphone. We use laptop, right? Going backwards, we have TV, we have movie. So smart vehicle is emerging as the fifth screen in our everyday life. Okay, so if you look at a modern car, people ask this question: this is a car or computer? And I know our distinction alumni, Hope, is in the audience. She's with Tesla. If we ask you, right, what is, a modern car is a computer, is a computer, is a car. So if you ask Tesla people, right, Tesla investors, and they're going to tell you this is a computer, okay? So smart vehicle is computer on the wheel. Okay. As I just mentioned, Edge AI finds great applications in autonomous driving, okay? Because a self-driving car would generate tens of gigabytes of data per mile, and it's infeasible to transport the data back to the cloud, okay? And more importantly, driving decisions have to be made on the spot in real time, on the order of like seconds, okay? And we go one step beyond autonomous driving, we look at connected vehicles as well. So there's this analogy between self-driving car alone and the connected and automated vehicles. So self-driving car alone is more like a nerdy student with high IQ and not so great EQ, right? That's perhaps explains why, Tesla, Uber, right, Volvo, and they do well in most cases, but once in a while we hear news about the car accidents, right? Okay, for connecting the automated vehicles, because they can talk to each other, they can exchange information, they get a better, more global view of the driving environment, the working concert, they can do better. Okay, so in our group, we are trying to work on Edge AI, and we are trying to push AI frontier from the cloud to internet edge. And there are many challenges. That's because each local edge has limited computational power compared to the data center in the cloud, right? And each local edge has a limited amount of local data, okay? So we are trying to develop a foundation for Edge AI to tackle these challenges and to develop AI algorithms capable of learning quickly with small data sets, okay? And another major effort in our group is we are trying to build a technology and a policy center for CAVs. We are also doing developing testbed. Okay, so let me elaborate a little bit. Okay, first, for Edge AI Foundation, so the idea is to accelerate online learning with offline training. This is very much inspired by the philosophy behind AlphaGo, AlphaZero. Okay, so in AlphaZero, AlphaGo, right, they first train a strong offline player. Then for online playing, they use quick adaptation to find the best strategy moving forward. Okay, so we are taking the same philosophy to develop Edge AI algorithms. And for autonomous driving, so we focus on offline reinforcement learning and use offline reinforcement learning to improve online vehicle automation. So we look into issues related to safety, sample efficiency, and the generalization, so on and so forth. Let me skip this. As I mentioned in passing, another effort is to build a synergy between technology and the policy, because for driving, autonomous driving in particular, safety, right, is most important, and the policy plays a very critical role to make sure so convergence of sensing, communication, control, and AI. Okay, how much time I do have? Okay, yeah. So we do both hardware and also software. And this is, just illustration of the test bed we have built. And this is the corresponding software architecture for the convergence of communication, control, and computing. Okay, so we are also building a software platform that has many modules for different functionalities, such as sensing, perception, communication, control, and also AI algorithms, for sure. Thank you.
Thank you, Junshan, for the very nice presentation. In the interest of time, maybe we can move on to the next new faculty presentation, which is going to be given by Professor Avesta Sasan, and he's going to talk to us about use of applied learning to solve challenging hardware security problems. Avesta is an associate professor in the ECE department at UC Davis. After receiving his PhD from the University of California at Irvine, he worked in industry at Broadcom and Qualcomm. He joined academia in 2016 as an associate professor in the ECE department of George Mason University. In 2021, Avesta joined the University of California at Davis in the ECE department, and we're happy to have him here among our colleagues. Avesta's research interest spans hardware security, machine learning, hardware design and acceleration, applied learning in VLSI and CAD, and the Internet of Things. Without further ado, I'll turn over the podium to Avesta to talk to us about his work. Thank you.
Well, good afternoon. Can everybody see the screen?
Yes, we do. Go ahead.
Great. Use of applied learning to solve challenging hardware security problems. My name is Avesta Sasan. I'm an associate professor with the ECE department at University of California, Davis, and I just joined UC Davis in 2021. I manage the Green Accelerated and Trustworthy Engineering Laboratory. And I thought since this is new faculty presentation, I just take a minute to talk about myself and then go to the presentation. I'm a UC system graduate, bachelor's, master's, PhD from University of California, Irvine. But also I have worked in industry since my senior undergraduate year, starting with Jazz Semiconductor in 2004, working in a clean room on automation and technology mapping, mostly night shifts until 2008 to support my undergraduate and probably master's studies. I moved to NovellX in 2008 doing memory and compiler design. Then 2009, I joined Broadcom, working on physical design, SoC design, and EDA design with 20 plus tape outs, being chip lead for a few of them. I moved to Qualcomm in 2014, doing research and development in VLSI technology group and designing in-house EDAs for yield, IR, and timing analysis until I changed course in 2016. And I joined academia, joined George Mason University, was there for 5.5 years until I joined University of California, Davis in 2021. My research spans two areas of hardware security and machine learning, and my research was sponsored by a number of funding agencies. What I really love to do most is to work at this cross-section of machine learning and hardware security. On the learning side, I'm looking at the security of the learning models, on efficient implementation of learning models for edge devices, IoT devices, real-time system and resource-constrained devices. I'm also working on learning-assisted VLSI design and digital design and physical design. And also a good portion of my research is focused on designing hardware accelerators for learning models. On the security side, I am doing logic IP protection, learning-assisted hardware security, Trojan and malware detection, key management, designing secure architectures, and also designing attacks for assessing the security of the hardware solutions in forms of logical, side channel, and physical attacks. And with that, I guess that brings me to the title of this talk. Just give me 1 second. I have, okay, there you go. And this brings me to the main topic of this talk, use of machine learning in hardware security. To better understand the type of hardware security issues that my team is working on, let me start by giving you a big picture of IC supply chain and explain what are the security and trust challenges that exist in a globally distributed supply chain. We have 2 models for IC development, a horizontal model and a vertical model. In the vertical model of IC development, one company is in charge of development of intellectual properties, design, physical design, fabrication, testing, packaging, integration. It's one company, therefore they could implement various strict monitoring and trust policies in place. Unfortunately, there are only 2 companies capable of doing that today, Intel and Samsung. Everybody else have to rely on this globally distributed supply chain where different stages of design, physical design, fabrication, testing, packaging, and integration happens by different entities that are globally distributed throughout the world. The reason for that is economy of a scale. We want to spread the risk. We want to scale on demand. We want to reduce time to market, always have access to best technology nodes, et cetera, et cetera. So these are all good, except the fact that when we are in a global distributed supply chain, there exist less trusted and untrusted entities in supply chain, and that has created and raised a lot of concern about the security and trust of the resulting ICs. Problems such as counterfeiting problem, cloning, hardware Trojans, IP piracy, IC overbuilding, reverse engineering, and modification to the process and package, to name a few. My research team has been looking at solutions to protect against many of these threats by coming up with different solutions and also coming up with novel attack vectors to try to assess the security of existing solutions. One of the areas that I want to talk about today is logic locking and FSM locking. So let me first formally define what logic locking is. It's making the functionality of your design dependent on a key value, such that if you have n bits of key values that are 2 to the power of n different possibilities, and only when you provide it with the correct key, the functionality is reduced to the intended one. We have come up with large number of solutions in this domain, and perhaps this is one of the best funded areas of my research. And we are looking at use of machine learning to basically create new logic obfuscation solution, more specifically use of reinforcement learning. But that's not what I want to talk about today. I want to talk about the part that we look at the security of this logic locking solution by means of developing attacks. And machine learning has been a very effective means of assisting us to develop very intrusive attacks. The objective of logic obfuscation is to build a solution that is very difficult, exponential difficulty, that when you put this most effective logical attack, such as satisfiability attack at work, the model is still protected. Why we use attacks? Because there is really no formal model to verify the resistance. However, when we try to basically come up with solutions, we have to run these attacks very often. But when you run these attacks on bigger benchmarks, on bigger obfuscation solutions that even pose like a polynomial complexity, not an exponential complexity, it would take a very long time for the attack to recover the key, and that prevents us from doing a lot of design space exploration. That is due to the SAT's random assignment of literals and random exploration of the search tree. Now, this was an area that we realized that we can effectively use machine learning. So we train a machine learning solution on a suite of a small obfuscation benchmarks for prediction of these literal values. And then when we are working on something that is larger, on a larger problem, we run this machine learning model on the side by side by our attack algorithm, and we ask the machine learning model to provide the SAT solver with initial seeds, with suggestions on which branches of the search tree should be exploited first. And we have shown that these could effectively reduce the runtime of a SAT attack by a few fold. I also want to mention that my team is one of the few teams that have developed these type of attack mechanisms. And we have, for example, satisfiability modulo attack and the rain attack that is used almost by every researcher now for evaluation of their logic obfuscation solutions. And these attacks are all openly available to the researchers, and they are downloadable both through GitHub and also in the webpage catforassurance.org if you're interested to know more about them. Next topic that I want to talk about is hardware Trojans. First, let me define what a hardware Trojan is, and then how we have used machine learning to detect hardware Trojans. Hardware Trojan is a malicious modification to a netlist to adversarially control its behavior, to bypass its security, or to steal secret information. What you see in this slide is a hardware Trojan used to bypass a crypto engine. So you can basically direct a plain text without encryption to an output port and read it in the plain sight. How can we detect hardware Trojans? Well, based on Heisenberg principle. Heisenberg principle, also known as observer effect, says that any attempt to measure or monitor a system changes its behavior. Now, we know that hardware Trojans are adding to the delay of timing paths. So one way to find hardware Trojans is by means of doing delay measurement, side channel delay analysis. To do that, we can collect the delay of a timing path, compare that with what we expect at design time. So test it, compare it to what we expected it. And then we use that increase or reduction of delay as an indication of a hardware Trojan. But it's not that simple. At design time, we have a biased view of the delay for two reasons. One, the design file that is provided to us by the foundry contains some added margins. Second, for designing an IC, we rely on a technology file that is given to us today, but we're going to work on this design for many months and fabricate it maybe in 8 or 14 months from now. Note that the process does not stand still, and it's going to change drastically over the course of the next 18 to 14 months. Therefore, the degree of correlation decreases, making it more difficult to detect these Trojans. But machine learning is here to help. Therefore, don't be disappointed. Here is how we can use machine learning. We can train a learning model to track and predict the nonlinear and feature-dependent delay transformation of each timing path. And when that's the case, we can first create a training set, and that training set is easily created by extracting features from the design and then getting the delay from the design, getting the delay from the tester, finding the difference between the two, and using that difference as a label. Now we have a training sample. We can collect many training samples. Then we have a data set. We can use that data set to train the model, and later on use that trained model for detection of hardware Trojan. How? We extract the features, we provide the features to the model that we train. It basically gives us a suggested shift in the value. We get the delay from the timing path, we deduct it from what we get from the tester. If the difference is large, then it's an indication of a hardware Trojan. This is a research that was sponsored by DARPA. But again, this is not as simple as I explained, because I try to simplify this. So a lot of additional steps have to be added on top, such as statistical noise modeling, design sensitization, management of airdrop and noise. And then you can basically bring this learning assisted clock frequency test that I explained into the picture. But also to make it a little bit more accurate, we realized that we cannot rely on a human to design the input features because, still although we claim that we are experts, we don't know everything. So what we decided to do is also to use machine learning for feature engineering. And that was by another form of machine learning called representation learning, taking all the information from design and then allowing the machine learning model to combine these features together to basically create more complex features that could be used in that machine learning model. So let's move to perhaps the last area that I guess, given the short time that we have, I want to cover, and that's detection of counterfeit electronics. So, and when I talk about counterfeit electronics here, I want to talk about aged ICs. So what is the problem? What is the aged IC? What is the aged counterfeit IC? Seeking profit, an old IC could be refurbished by profit seeker and illegally supplied back to the market as a new product. These counterfeit ICs are aged, they are unreliable, and when you use a counterfeit IC that costs $1 in a system, in a large system, the result could be catastrophic failure of a system worth thousands or millions of dollars, and perhaps even more catastrophic results. To detect counterfeit ICs, we also relied on machine learning. What we observed is that within the same IC, not all areas of the IC age the same, not all timing paths within an IC age the same. So we made this observation, and then we collected two sets of areas, two sets of timing paths within a design, a set that we think would age more and one set that we think would age less. And you can basically deduct that based on expectation of activity and the topology of the netlist. Then, similar to what we did for the hardware Trojan case, we trained a machine learning model to predict the difference between what is reported by the tester and what is reported at design time for one of these sets, the set that age least. And then we can use this machine learning model to basically predict the timing shift for both sets, for the set that age more and the set that age less. This gives us two different distributions. Now, from here on, the detection of aging becomes simple. If these two sets had the same distribution, that means the IC has not aged. If the distribution were slightly different, that means it's slightly aged. And if they are very different, that means the IC is very much aged. So not only machine learning helps us to detect aged ICs, it can also tell us how aged that integrated circuit is. Given that the time is limited, I would not be able to cover additional topics. Hence, I would just give you an overview of the hardware and ML security topics that my team has worked on, including use of ML for speeding up test and verification, for Trojan detection, for malware detection, for age detection, for counterfeit IC detection, for correlation and anomaly detection, for reverse engineering, for designing more effective attacks. And even we have looked at the security of the learning models itself. And also there are some new areas that we are investigating: microarchitectural attacks on ML systems, protection of ML assisted computing systems. For example, consider that you have a computer that you have replaced the branch predictor with a machine learning model. Now it works great, ML can do that, but now you have opened the system in addition to the previous existing microarchitectural attacks to new form of attacks against adversarial attacks against the machine learning model itself as well. We are looking at physical designs that are fully automated based on machine learning models, and how we can use like reinforcement learning agents to build security into the physical designs. the hardware architectures that protect the resident ML solution. So I guess these are all the topics that we are currently and actively are working on. Now, as a last slide, and in conclusion, machine learning has been a disruptive technology. It has affected almost every field that we can imagine. Hardware design, hardware security, and computer security are no exception. Machine learning has enabled more powerful defenses, as you have seen in a few of the slides that I have presented. But at the same time, it has also created more intrusive attacks. It has helped solving many old problems, but has also created many new challenges. And this game is not close to ending, but my time and my presentation is. So with that, I thank you for your presence and ask you to stay safe and secure.